This question is from the LO4 course notes for statics. The tutorial at the end is question 13. And so we're given a scenario where three plates are held together by two rivets. Now what we're seeing in the diagram here is a side-on view. We can only see one of the rivets here, and a top-down view where we can see both rivets, 1 and 2. And what's important to note about this is that we have two rivets, and each rivet will be in contact in two places with the plate that's moving due to the direct force. So that means when we come to think about the total area of shear, we have the cross section of each rivet being in shear 2 times each. So our total shear area will be 4 times the cross section of one rivet. Let's bear that in mind before we begin. So let's see what else is going on in this question. Well, the force that's been applied directly to the plate and in shear to the rivet is given as 10 kilonewtons. So we can make a note of that just now. It's a 10 kilonewton force. And we're told that the shear stress is not to exceed 50 newtons per millimeter squared. So we can actually use this as a value in our calculation. If we base our calculation on this maximum value, then we can work out what area is permitted for this particular combination of stress and force. So we can find out what area would be big enough to keep this 10 kilonewton force limited to a stress of 50 newtons per millimeter squared. Before we do this calculation, we need to make sure we're working in consistent units. So we'll change our 10 kilonewton force to 10,000 newtons. There's no problem working in millimeters. We have no other quantities given to us. So we can leave tau, our shear stress, is 50 newtons per millimeter squared. What this does mean is that our area, once we calculate it, will also be in millimeters squared. So consistency of our units is incredibly important. From the course notes, we know that tau is equal to force divided by area. And therefore, rearranging this, we have area is equal to force divided by tau. So carrying out this calculation, we have 10,000 divided by 50. And this is not a particularly hard calculation to do, but it's always best to check these in our calculator when we're doing an assessment question. So I'm sure if you can work out that's 200, that's great, but why risk it? We have 200 millimeters squared. And I should say that's the total area. So let's make clear with this. The area is under shear. Area total or area shear is 200 millimeters squared. Now, as I said at the beginning, we know that the area under shear is 4 times the cross section of one rivet. There's 2 rivets, and each rivet is sheared in 2 places. So the area of a rivet will be our total area divided by 4, equal to 50 millimeters squared. And we're assuming, although we don't need to state this, but we're assuming that both the rivets experience shear equally. Now, we're asked to find the diameter of the rivet. Well, if we know the area of the rivet, finding the diameter is a matter of using this formula. Area is equal to pi e squared over 4. We're choosing to use this version because we're asked to find diameter. Entering 50 for a value for A equal to pi times d squared over 4. You're also welcome to transpose the formula beforehand if you prefer to get a formula for D. This works too. We're going to get 4 times 50 divided by pi is equal to d squared. And so d is equal to the square root of 4 times 50 divided by pi. And I suspect this will give us the answer the course notes is indicating, but there's no reason not to check it in our calculator. So take the square root of 4 times 50 divided by pi, and we get the answer of 7.98. And because we were working in millimeters squared for our area, that means our diameter is in millimeters as well. And as we hope for, this gives us the answer indicated in the notes. That's how we go about solving a question like this. And the key thing is to work out how many times the cross-sectional circular area of the rivet adds up to give our total shear area.